Okay, here we're going to talk about exponential expressions, and we'll first consider the expression 2 to the x. Now the variable is in the exponent as opposed to, for instance, the expression x squared where the variable is in the base. So let's look for solutions to the equation y equals 2 to the x and understand how to evaluate basically these expressions. So remembering that solutions are order pairs of numbers, a, b, so that when we plug in a for x and b for y, we get a true statement. We see, for instance, if we plug in 1 to the right-hand side, we get 2, but if we plug 1 into the left, we get 1. Since 1 is not equal to 2, 1 comma 1 is not a solution. If we plug in 0 for x and 1 for y, we do get, indeed, a true statement because 2 to the 0 is 1. We can actually evaluate the expression on the right-hand side for various values of x and find the corresponding values of y. For instance, we already found that 0, if we plug in 0 on the right-hand side, we'll get y equals 1. If we plug in 1 on the right-hand side, 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the negative 1, remember what negative 1 as an exponent means. It's a reciprocal. And 2 to the negative 2 is 1 over 2 squared, which is 1/4. So in this way, we get 6 ordered pairs of solutions to this equation, and we can graph it. We graph each of these points. This is not super precise, but it gives you an idea of the growth of the set of solutions as we look from left to right. Perhaps you've even heard of the term exponential growth. The expression on the right is called an exponential expression, and this is seeing that growth. The larger the values we plug in into the right-hand side, the larger the values of the left-hand side. So I just want to point out that we can look at, for instance, y equals 4 to the x, and we can rewrite that as 2 to the 2x. So this is kind of like a stretch factor in the x-axis. We're multiplying the x by 2, which is similar to squishing the graph in the x direction, so compressing it. The reciprocal is 1/2. The compression factor is 1/2, which is equivalent basically to replacing the tick marks 1, 2, 3 by 1/2, 2 halves, 3 halves. The graph of y equals 4 to the x looks just like the graph of y equals 2 to the x, except for the tick marks on the x-axis, or that it's compressed in the x direction. So in general, the graph, when the base is bigger than 1, looks exactly like the one we graphed. When b is less than 1, we can also look at the reciprocal and make sure we put a negative sign in the exponent. Now 1 over b is greater than 1, so we see that this is a reflection of the x-axis. Just like we had in the parabola case, a minus sign in front of the y will give us a reflection of the y-axis. This one, by the way, is kind of a picture of what they call exponential decay. So when the base is less than 1, we get decay as we move from left to right in the picture. On the left-hand side, we get growth. That's when the base is bigger than 1. So next we define the expression log base b of a. That's just a way to say that, log base b of a. These things are inseparable. This is one expression which we will define all at once. It depends on two numbers, b and a. And we're just going to define it to be the solution to the equation b to the x equals a. This is very similar to defining the square root of a to be the non-negative solution of x squared equals a. So the square root of a is a non-negative solution of x squared equals a. So this is analogous. So we're going to define this to be a solution to an equation. There we are. Okay, graphically, for instance, if we want to find log base b of a, we can set both sides equal to y, so that we're looking for an intersection of two graphs, and our solution to this equation is exactly the x-coordinate of the intersection of these two graphs. We know that that exists as long as a is bigger than 0. And we know that there is one solution. So this will be some definite number, provided a is bigger than 0, whether the base is greater than 1 or less than 1, provided the base is positive. Okay, so let's look at an example. Log base 2 of 8 is the solution to this equation, but we know the solution is 3. So that means log base 2 of 8 is 3. Let's look at log base 5 of 1 over 25. That's the solution to this equation, but we know we can write 1 over 25 as a power of 5, 5 to the negative 2. So we see that one solution is negative 2, but there is only one solution, so negative 2 is the solution, and log base 5 of 1 over 25 is negative 2. Log base b of 1 is 0, since b to the 0 is 1. Log base 10 of 5 is the solution to this. Now that's a little tricky, because none of the numbers we try gives us 5. We can't find a solution, but I do want to point out that your calculator knows the answer. There's a log button on your calculator. Log means log base 10. So I want to point out a similarity in what we discussed before with the calculator now. So the solution to x squared equals 5 can be solved using the square root button, and just like that, the solution to 10 to the x equals 5 can be solved using the log button. Log base 10 of 5 is the solution to this equation. Square root of 5 is the solution to this equation, and we operate similarly with the calculator. Note that log and 10 to the x share a button, very likely anyway on your calculator, just like x squared and square root of x share a button. By the way, natural log, that's ln, and e to the x also share a button, so we will also see that the ln button will solve equations that look like e to the x equals a. So, by the way, natural log of a is actually log base, that should be ne, of a. E is a very specific number we won't get into right now. How do you solve this on your calculator? You take log of 5. I'm not sure what we get. We'll have to check on a calculator. So log base 10 of 5 is a solution to 10 to the x equals 5. I just want to draw your attention to the similar problem of this x squared equals 5. How do we solve that, at least get the non-negative solution? We take the square root of 5. The square and the square root button are the same button. Okay, so the one button squares, the one and the same button will actually solve the equation that looks like x squared equals 5. Okay, similarly, to solve this equation, so to find log base 10 of 5, we just use the button that is shared with 10 to the x, which is log. So we will take log of 5. So your calculator can solve that, and we find out that log base 10 of 5 is approximately 0.699. I do want to point out that this is an approximation. The actual answer is just log base 10 of 5. Okay, and I want to point out some other similarities on your calculator. So, like I pointed out just a moment ago, these share a button, these two share a button, and also these two share a button. So that leads me to say that natural log ln of a, natural log of a, is equivalent to log base e of a. So, for example, natural log of e squared is 2, since e to the x equals e squared has 2 as the solution. We don't really have an idea of what e is. It's some number. We'll see a little bit of that in the next section. So for now, I want to just give properties of exponents and of logs. We already know the properties of exponents, but there are corresponding properties of logs. So b to the 0 is 1. If we write this as 0 as a solution to b to the x equals 1, what we're saying here is log base b of 1 is 0. Here is the property of exponents, and the corresponding property of logs is this one. This means the log of a product is the sum of the logs, and we can see that by noting that the left-hand side is if we let u equals b to the x and v equals b to the y, then this statement here says that uv equals b to the x plus y. So this uv is b to the x plus y, which means the left-hand side is x plus y. The right-hand side is x plus y. Looking at this property, so the left-hand side of log base b of u to the r is equal to xr, because u to the r is b to the x to the r, and by this property, the exponential property, that's equal to b to the xr, which means that u to the r is equal to b to the xr, so log base b of u to the r is equal to xr. So the left-hand side is xr. The right-hand side is also xr, because it's r times log base b of u, which is x. And finally, there's a change of base formula. So r is equivalent to r. So a to the log a of r is equal to b to the log b of r. But b is this expression. This is the property of exponents. So putting these two together, that equality right there, we get this. And so dividing both sides by log base a of b, we get this expression. Notice that the right-hand side has two logs, both of base a, and the left-hand side has a base b. That's why it's a change of base formula. We'll do an example below. Here's the summary of the properties of logs. I just rewrote them here. I did add one more property, which is b, which is just a combination of this when r is -1, and this one which we discussed also. So in this case, if we have division, this is the same as x times y to the -1, and then we can use this property to pull the minus out in front. Okay, so here's an example of the change of base formula. If we have log base 5 of 7 and we want to approximate that with our calculator, we are, with most calculators, stuck at this point. However, with the change of base formula, we can write this with a new base of 10, which is on our calculator. There are only two log buttons on a typical calculator. That's log, which is log base 10, or ln, which is log base e. So we can write this using our change of base formula, which is number 4 here. And that is log base 10 of 7 over log base 10 of 5. We put that in our calculator. I recommend you try it to make sure you know how to use your calculator. You will get 1.209 approximately. As soon as you use your calculator, by the way, you don't have an equal sign anymore. You have something that's only approximate. Here's another example. I'm going to try to keep these visible while I do this example. So this is log base b of this expression. Okay, and I'm going to expand it in terms of logs of x, logs of y, log of z. So log base b of this is the same as this. That is using property 2. Turns a product, which is right there, into a sum of the logs. Then I deal with these exponents using property 3. So now these exponents appear as multipliers in front of the respective logs. And then I use property 2 again, because this is a product. I can write it as a sum of the logs. And what we have is our final answer. And why is that our final answer? Is because log x appears, log y appears, and log z appears. Nothing more complicated than x, y, and z in these log expressions. Let's do another example like that. Log base 7 of this expression. Let's break it up using property 2, a and b. Property 2a tells us if it's a product, it comes with a plus sign. If it's a division, it comes with a minus sign. Ultimately, that means if it's in the numerator, you have a plus sign in front. And if it's in the denominator, you'll get a minus sign in front. So you write a product and division as sums and differences of logs. And then we deal with the two exponents here. We're using property 3. And we have now succeeded in writing our original expression as a sum of simpler logarithms. Now let's go the other way. Let's write this expression that has the simple logs in terms of a single logarithm. We basically go in the order reverse of what we did in the previous example. Or the factor of 2 becomes an exponent using property 3. I'm going to distribute the 1/2 into this term and this term, and also make that factor an exponent. This becomes a minus 1/2, so this is the exponent of minus 1/2, which means it's a reciprocal of the positive exponent 1/2. And 1 I write as log base 2 of 2. So now everything is written as logs. So now I see differences and sums, and accordingly I will put things in. If it's got a positive out front, it's in the numerator. So these are in the numerator. This is also in the numerator, except that it's already in the denominator. So that belongs down here. So those are the plus signs. They stay in the same place they are. And the minus signs will go into the denominator. And then writing this as a square root of z over w, we get our final answer. And this has only one logarithm in it. One term, one logarithm. Maybe it's easier to keep this way. That's equivalent. So now I did not bring the minus sign up with the exponent, and you can see that that is in the denominator.